Yo, what's up? Brainy Nerd Tutor here, and we're going to go through stoichiometry, some stoichiometry problems. This is a massive review that I've prepared for you. We're also going to discuss molar mass, solution stoichiometry, grams to moles, and I'm going to take you through this step by step through chemistry, stoichiometry stuff. And we're going to start off at the very basic things that you need to know to warm you up to stoichiometry. So this is for complete beginners. And after this, if you go through this and understand what's going on, then you'll be the goat on your stoichiometry exam. You can goat it to your friends. Anyways, just getting stupid now. All right, so to begin with, we'll start off with the mole. And the mole is really just a number. Now, your teacher won't say it's just a number, but it's really a number. Just like the word dozen. Dozen is a number. Dozen means 12. You could have a dozen eggs. You could have a dozen bananas here. And I have this listed here. So a dozen is 12. And in scientific notation, it's just 1.2 times 10, 10 to the power of 1. We could also have another word that we're used to. That's a number, 100. 100 is a number. You could have 100 eggs or 100 bananas. That's just a number 100 or 1 times 10 to the 2. And or a million, for example, the word million means that it's 1 times 10 to the 6. It's just a number here. And the mole, too. The mole is really here, when it comes down to it, it's just a number. 1 mole means 6.022 times 10 to the 23. Now, when you say 1 mole, you got to say it's 1 mole of what? So you can have, say, that's 1 mole of bananas, which is a lot of bananas. There's probably not this many in the world. Or a mole of eggs would be this many eggs. Just like when you say 1 million, it's this number here, 1 mole. Now, we use moles because molecules and atoms are really, really small. So we can't count them by the dozen or the 100. That's why we count them by the mole. The mole is such a huge, large number. So you can have a mole of atoms. Here, so each dot here represents an atom, or a mole of molecules, that sort of thing. Now, a mole is a number, but when your teacher or your prof says that it's more than just a number, they also mean that it's a unit as well. It's a unit of counting a number. So, for example, dollars. You can count how much money you have in terms of dollars, or you can count it in terms of cents. Well, dollars is the unit of a quantity of your currency. Here, rather than counting molecules one at a time and saying we have like this many molecules, it's more convenient to say we have this many moles. So the mole, it's a internationally recognized unit for the number of something, but it could be a number of anything, really. Okay, so that's a mole. Next thing before we get into stoichiometry is molar mass. Now, if you look at this scale that I have here, we see that a dozen bananas weigh more than a dozen eggs. Or I'm pretty sure it weighs more than a dozen eggs. I've never done this myself. If anyone wants to go out and measure it and let me know in the comments, that'd be pretty funny. But anyways, they don't weigh the same quantity or the same amount, but not the same mass. To get the same mass, obviously we would need to have less bananas or more eggs. So in this case, if we have the same number of eggs, we can say have 6 bananas rather than 12. Maybe this weighs the same. I don't know. I haven't tested it. But this is very similar to what we do with molecules here. We can have the same number of objects, but their masses will be different. So here's a photo that I took in the lab. This is a mole of sodium chloride, which is table salt. 1 mole of this many molecules. Now, as a solid, it's not really molecules. You're dealing with formula units, but we'll just pretend that these are molecules here rather than formula units, so we don't get into that. But a mole of sodium chloride is about 58 grams, and this is it. This is its volume. This is how much it weighs. But a mole of this compound here, this is sodium bicarb, which is just baking soda, is a lot more. It's about 84 grams. So both of these beakers have the same amount of substance, the same quote unquote number of moles of each. But this one is heavier. See how there's more atoms in here and stuff? I know chlorine's heavier than the other ones, but there's just overall, this is heavier for every one of these compared to one of these. Therefore, to get a mole to the same number of each, we need it be a greater volume here. So this would be more mass. Okay, so that's molar mass. Now, let's calculate grams to moles. We'll calculate molar mass as well as we get into it. So grams to moles is what you'll need to know for stoichiometry. So we'll start off putting our training wheels on. How many moles are in 15 grams of carbon? So we want to go from grams to moles here. And we do that using our friend or enemy, but soon to be friend, the periodic table. Now what you're seeing here, this is from ptable.com. And it's nice because up here in this corner, it shows the element. If I highlight the element, it just shows it. And what we want, I'm going to go back. We want to know how many moles are in 15 grams of carbon. So I'm going to go to carbon and hover over carbon. And you see we're on the top left there, that bottom number, 12.011 grams in the big green square, 12.011 grams. That's how much 1 mole of carbon weighs, 12.011 grams. So I can write here, so we can say 1 mole of carbon, and we always got to say mole of what? It's like bananas or carbon or whatever it is. We're going to say what it's a mole of, is equal to 12.011 grams of carbon. So these are equivalent. If you have 1 mole of carbon, then it weighs 12.011 grams. So they're essentially the same, just different units here. So if we want to know how many moles there are, so we'll start off with 15 grams, because this is our given, grams of carbon, and we want to know how many moles. Well, if these are equivalent, see this number here? We can multiply this number by 1 over 1. And it doesn't change, right? You can multiply anything by 1, it doesn't change. Multiply it by 1, divide it by 1, nothing changes here. Well, 1 and 1 is the same. So multiplying it by a fraction with the numerator and the denominator are the same. We don't change this at all. So since these are the same here, these moles, this mole and gram conversion, we can write this as 1 mole of C divided by 12.011 grams of C. And by multiplying this 15 grams by this fraction here, we're not changing it per se. We're just changing the units because the numerator and the denominator are essentially equivalent. Now here, grams cancel out. And see, this is a fraction on this side, but this is also a fraction. This is like divided by 1, because any number is like divided by 1. So it's like grams is in the numerator. And I didn't write this, I kind of wrote this messy in a way. 15 grams of C, there we go, times. So this is like divided by 1. So this grams of C cancels out with this grams of C. And then we just divide. So 15 divided by 12.011. 15 divided by 12.011 is 1.25. 1.25 moles of carbon. So that's how many moles of carbon you have. This says 2 sig figs, so we'd round this up to 2, round it down 2 sig figs. So 1.2 moles of carbon. If you round it up to 3, 1.3, you'd probably get the right answer too. You wouldn't lose marks for sig figs. Okay, so we'll do this again. How many grams are in 3.4 moles of CO2? So we need to know the equivalence. How many grams 1 mole of CO2 weighs? So we'll go to our trusty periodic table, and we go to carbon here. Carbon is 12.011, and CO2 also has O in it. So I'm hovered over O. You can't see it, but you see that square in the top left? The molar mass, or the mass, the amount of the 1 mole of oxygen weighs 15.999 grams. So to get the molar mass of that, we would say it's 12.011 grams per mole for the carbon, plus 2 times 15.999 grams per mole. That equals, I think it's 44.0. Keep going to the periodic table. So 12.011 plus 2 times 15.999 is 44.009. 44.009 grams per mole. So this means that 1 mole of CO2 weighs 44.009 grams. This is the molar mass of CO2. Okay, so now we have this many moles of CO2, 3.4. So we have 3.4 moles of CO2, and include this CO2, that's important. It's pretty obvious in these kind of beginner examples that it's CO2, but later on, it's not that obvious sometimes. Now we want to get to grams, right? So what I always recommend is put the units in first. We want moles to cancel out. So we're going to put moles of CO2 in the denominator because we want that to cancel out here, and we want grams. So we're going to put grams of CO2 in the numerator. Do the units first, and then our units will always cancel. So moles, they cancel. Now there is in 1 mole weighs 44.009 grams, and our moles cancel. Cross this out too, just for your own satisfaction. 3.4 times 44.009 is 149.6. 149.6 grams of CO2. Again, we have two significant figures, so we'd round this up to 150 grams of CO2. All right, moving along. So how many moles of Cl, so this is chlorine, are in 5.4 grams of magnesium chloride, MgCl2? So we want to go from grams to moles, and we don't want moles of this, we want moles of chlorine. So first, let's deal with this MgCl2 first, just like what we did before. So magnesium has a molar mass of 24.305. See that top left square? 1 mole of magnesium weighs 24.305 grams. So this is 24.305 grams for every 1 mole. Plus, now there's 2 chlorines for every one of these. So we have to do 2 times, and the molar mass of chlorine is 35.45 grams. So times 35.45, that's how many grams are in 1 mole of chlorine. So we're adding this up. This gives us the molar mass of MgCl2, 24.305 plus 2 times 35.45, 95.205. So 90, did I say 95? 95, yes. 95.205 grams per mole. So what this means is 1 mole of MgCl2 weighs 95.205 grams of MgCl2. We'll go from grams to moles of magnesium chloride. So we'll start off with 5.4 grams of MgCl2. And we'll go to moles. Just like before, we'll multiply it by the fraction. And we'll put in the units first. So there's moles. We want moles. No, this is in grams. So we want grams in the denominator. Grams of MgCl2. We want moles in the numerator. See, I almost screwed up there. Almost made a fatal error by I almost just instinctively put moles down here, which is wrong. So I'm glad we did the units first. So we know that these units cancel. Now in 1 mole, that weighs 95.205. Can I squish this in here? 95.205 grams. And we're left with moles of MgCl2. But we don't want moles of MgCl2. We want moles of Cl. We want to know how many atoms, how many Cl's there are. Well, we know how many MgCl2s there are, and we know how many Cl's make up one MgCl2. Like if you have magnesium here and it's bonded to 2 chlorines, this is basically what we have. We have 2 chlorines bonded to a magnesium. So for one of these, to make one of these, we need 2 Cl's. So our conversion is for every 1 MgCl2, we need 2 Cl's, right? We need 2 Cl's to make up 1 Gl2. Now, we're not talking about 1 molecule because we need to deal with things in moles. So 1 mole, MOL, and I don't know if you notice this, but usually we leave off the E. Just, I think it's, maybe chemists think it's cool or something. Mole, rather than writing the E. We're lazy, I don't know. But you write things in terms of mole. So if we have a mole of this, if we have a dozen of this, we need 2 dozen chlorines. If we have 100 MgCl2s, we need 200 chlorines. If we have 1 mole of MgCl2, we need 2 moles of chlorine. And this is our conversion between these two. So we have moles of MgCl2, but we want moles of chlorine. So we'll multiply this by our factor. Now we want to cancel out moles of MgCl2, so we'll write that in first. Moles of MgCl2. Sorry, this is messy. and we want moles of Cl. That's what we want to end up with. And there are 2 moles of Cl for every 1 mole of MgCl2. MgCl2 cancels out, and we're left with this here. So just calculate this in the calculator. 5.4 times, divided by 95.205 times 2, 0.1134. So I'll write in 0.1134. And what are our units? Moles of Cl. 2 sig figs. We're given two digits here, so our answer is 0.11 moles of chlorine. All right, so the most basic introduction to stoichiometry is with moles to moles in a chemical reaction. So now that you know what a mole is and what molar mass is and how to convert between mass and moles, we're going to do, this is actual stoichiometry start. And to start off, we just deal with moles to moles. So this is our first example. How many moles of oxygen gas are produced from 6.0 moles of, this is potassium chlorate. Anyways, you don't need to know that, KClO3. And this is, we have a balanced chemical equation here. Now it should be balanced, double check, because sometimes your teacher or prof tries to trick you. Most of them don't, but some do. And it's balanced, so it looks good. So what we have here, we have a chemical equation, and we want to know how many moles of oxygen. So here's oxygen here. So we want to know moles, how many moles of this we get. But we're given 6.0 moles of this, 6.0 moles of KClO3. Now, these numbers here in this chemical reaction, these numbers tell us the ratio of how the compounds react. Now, I know that maybe sounds complicated, but all it means is if you have 2 molecules of KClO3, 2 molecules, okay, just 2 molecules, you can make 3 molecules of oxygen. If you have 2 molecules of this, you can make 2 molecules of this. Now, we don't have 2 molecules of it. We have 6 moles of this. But what this is saying is that for every 2 molecules of this that reacts, we make 3 molecules of oxygen. If we react 200 of these molecules, then we will make 300 molecules of oxygen. That just tells us the ratio in which they act. So this is a 2 to 3 ratio in this chemical reaction. So if we have 1 mole of Kl, not 1 mole, let's say 2 moles. If we have 2 moles of KClO3, we'll produce 3 moles of oxygen. So these numbers here give us a mole conversion between these compounds in the chemical reaction. And since we want to know information about oxygen, given information about KClO3, we got to go from moles of KClO3 to moles of O2. Our conversion here, just like what we did with grams and moles, is 2 moles of KClO3 equals, now this really isn't equals. I'm not sure if any mathematicians are watching this video, but it helps us set up this relationship. 3 moles of O2 gas. So there's a 2 to 3 molar ratio, and this is what we do to convert between moles of each substance here. So we'll start off with what we're given is 6.0 moles of KClO3, and we want moles of O2. So we want moles of O2 on top, and we want to cancel out moles of KClO3, and we get 3 moles of O2 for every 2 moles of KClO3 that reacts. And then we should be able to do this in our head. There should be 9.0 moles of, so our moles of KClO3 cancel out, and we're left with moles of O2. Moles of O2. Still 2 significant figures, even though there's 1 digit here. These don't count because these are exact numbers, so they don't count for sig figs. Okay, let's do another moles to moles conversion to get a little used to it. So how many moles of oxygen gas can be produced from 4.0 moles of H2 here? And we have this balanced chemical equation. So we want to know moles of O2, again, moles. And we're given, this is our given, 4.0 moles of H2. So 4.0 moles, that's our given. So again, we have this 3 to 4 ratio. 3 moles of O2 react, and every time 3 moles of, 3 moles of O2 doesn't react. We don't know how many moles react, but for every 3 moles that react, we get 2 moles of H2. Say we only react half of this. If we react 1.5 moles of oxygen, we would get half the amount. We get 2 moles of H2. It's just a 3 to 4 ratio. So we can say 1 mole of O2 is equivalent to or produces, well, not 1 mole, sorry, 3 moles of O2 produces 4 moles of H2 gas. Okay, so we'll start off with our given. And there's a 3-step process I'm going to show you that works for every stoichiometry problem. Once we get into a little bit more complicated ones, it always works. It works with this as well, but you don't really see all 3 steps with these ones. But it's a very simple process, 3 steps for stoichiometry. You'll get it right every time. It's pretty sweet. Okay, so we're starting off with 4.0 moles of H2. Oh, you know what, we could just do this in our head because we need 3 moles of O2. Anyways, we'll do the math here. So we want moles. Oh, what is this? See, look, I made this error. I didn't write what this was of. This is 4 moles of what? Bananas? H2, 4 moles of H2, because we can't just cancel out moles. We have to cancel out moles of whatever it is. We got to make sure that if it's moles of H2, it cancels out with moles of H2. We can't cancel out moles of bananas, if this was bananas, and moles of eggs down here. That doesn't work at all. So that'd be weird. So we want moles of O2, and there's 3 moles of, every time 3 moles of O2 react, we produce 4 moles of hydrogen. So our moles of hydrogen cancel out, and so does the 4, so we're left with 3.0 moles of O2. Alrighty, so now we'll add another complexity, which you'll see on your exams, is stoichiometry with grams. So grams to moles, moles to grams using molar mass. So I'm going to show you my 3-step process. It's not really mine. It's just a very simple 3-step process that works. It's been used for decades, but maybe you don't know it or it hasn't been taught to you properly or that sort of thing. It's quite simple, and if you do it, then those 3 steps, you'll always get stoichiometry correct. So we're going to start off. We'll read the question. How many grams of O2? So we want to know grams of this are necessary to react with 4.0 grams of C3H8. 4.0 grams of this. We have 4.0 grams of this. How many grams of this? Now, there's no number here, which means there's a 1. There's no number. And this 1 to 3 means that for every 1 molecule or 1 mole of this, 100 of these, it reacts with 3 molecules or 3 moles or 300s of these. This isn't gram. It's not like 1 gram of this reacts with 3 grams of that. No. These are just moles here. So 1 mole of this is 1 mole of that. So, and this is stoichiometry. And you know this is a stoichiometry problem because you have a chemical equation, a balanced one, I was going to say, should be balanced. If not, you have to balance it. But you have a chemical equation. You're given information about one of the compounds. So in this case, we have information about C3H8, 4.0 grams. And we want to know something about a different compound, in this case, oxygen. If those criteria are met, this is stoichiometry, and this is the 3-step process to solve it every time. Step 1, you need to calculate moles of your given. Moles of given. What's our given? Well, this is our given. It's whatever we have the information about, the mass or the moles or the concentration, whatever, volume, things like that. So we'll go from grams to moles. We have 4.0 grams of C3H8. Now we want to go to moles, and to go to moles, we need to cancel out grams. So we need to know how many grams are in 1 mole of C3H8. So we'll go to our periodic table here, and I'm highlighting over carbon. Carbon has a mass of 12.011 grams for every 1 mole, and hydrogen has a mass of 1.008. grams for every 1 mole. So we'll put that on our calculator. So carbon is 12.011 times 3 plus 8 times, and each hydrogen weighs 1.008 grams for every 1 mole. So 44.097. And we want grams down here, grams of C3H8. And we want moles up here, because that's step 1, moles of our given, C3H8. And every 1 mole weighs 44 point, is it 097? 097. 097 grams. Okay. So 4 divided by 44.097, 0.090709. So 0.090709 moles of C3H8. Okay, so that's step 1. Not too bad. We've already done it a number of times. So step 2 is to calculate moles of your desired. So desired is the compound that you want to know about. In this case, it's oxygen. Oxygens are desired. We want to know how many grams are in oxygen. Now that we know how many moles of our given there are, we calculate the moles of the desired. And we've done this. So we're just going from moles of C3H8 to moles of oxygen. And we know that 1 mole of C3H8 reacts with 3 moles of oxygen. So we'll do just like what we did before. We'll do that fraction again, 0.090709 moles of C3H8. And we've got to go moles of our oxygen. So we want moles of C3H8 to cancel out. And we want moles of oxygen. And there are 3 moles of oxygen react for every 1 mole of C3H8. Moles of C3H8 cancel out. I could probably do this in my head. It's dangerous. 0.27. Oh, what's this? 221, I think. 21. I'll just stop there. Moles of O2. I can do this in my head because I know 3 times 9 is 27, and 3 times 7 is 21. So that's not too bad. Okay, so now that we know how many moles of oxygen there are, we need to go from moles of our desired, whatever it is we want, in this case oxygen, to the units that we want, which is grams. So that's step 3. And for each step, we use the answer from the previous step. So step 3 is the units of desired. I made a video on this as well, this step-by-step process in detail. If you want to check that out, went through it very slowly. Okay, so units of desired. So we'll take the number that we previously obtained, 0.2721 moles of O2. Now our units are in grams. So we want grams of O2. And to change this to grams, we need to cancel out moles. So moles of O2. And there's 1 mole for every 32 grams. So if we go to oxygen, hovering over oxygen, 1 oxygen atom, on average, weighs 15.999 grams per mole. So if we have 2 oxygens, we got to do, just going to move these units over. Grams of O2. We need 2 times 15.999 grams. You see that? 1 gram, 1 O2 weighs 15.999, but here we have 2 of them in the molecule, so we need to do 2 times 15.999. Okay, so, well, this one I can't do in my head. All right, so we have 0.2721 times 2 times 15.999 divided by 1, which I don't have to put in there. So 8.707 rounding. 8.707, and our units are in grams of O2, which is what we want. Grams of O2. So we'll go to the beginning of the question for full marks. Check for your significant figures. There's 2 sig figs here. So our answer has to have 2 sig figs as well. So you can either leave it as a line or write it like this. Actually, some teachers or profs might want you to write it like either this way or this way. It's the same, but there we go. 8.7 grams of O2. All right, moving along, another exam problem. Calculate the mass of C2H5OH produced from 500 grams of C6H12O6. This is glucose. This is um, ethanol, looks like. Okay, so we have a chemical equation. We have some information about one of the compounds. Here we have 500.0 grams. We want to know something about another compound. So the mass here. So this is stoichiometry. So we're going to do this, and I'm going to do these 3 steps kind of at the same time. So step 1, if you remember what they are, moles of desired, moles of given. And pause the video. Try this yourself, and then unpause it and let me know if you got it right or not. It's very instructive if you can work on it on your own. So moles of are given. Okay, so we're starting off with grams. 500.0 grams of, I'm going to call this A and call this B. Grams of A just because it's so long. As long as you define it like this, you should be okay to put it down here. I don't see any problem with that. Let me know if your teachers give you any crap for that, but I think it's fine. You're labeling it. Okay, so we want to know how many moles are in how many grams of A. Right, we want to cancel out grams, so grams of A, and we want moles of A. That's our moles of given, and it's C6H12O6. So we'll go to our periodic table, and carbon's 12.011, hydrogen is 1.008, and oxygen weighs 15.999 grams for every 1 mole. So we'll go in our calculator, and we'll multiply, add this up, 12.011, to calculate the molar mass of this compound, plus there's 12 H's, 1.008, and there's 6 oxygens, 6 times 15.999. I love these calculators where you can see what you type. Does anyone use these as well? I hope you don't use a one-line calculator where you can't see what you type. I used one of those one-liners kind of my whole undergrad, my first undergrad, and I don't know why I didn't switch. Spend the $10, get one with a line where you can see, because you'll save yourself from many mistakes. Anyways, 180.156 grams. So 1 mole weighs 180. That was it 156 grams. Okay, so this way we've canceled out grams of A. Now we know how many moles of A there are. That's our step 1. Step 2, now that we're in moles of A, we want to calculate moles of our desired. So I'll just write moles of desired. And our desired is this one right here. So we can actually, we don't have to calculate what this number is. We could continue the multiplication train here. It's called a conversion factor. Sometimes conversion factor trains. So moles of A, we want moles of A to cancel out. So we want moles of A down here in the denominator. And we want moles of B. Moles of B. And this equation here, see there's no number here. That means there's a 1. Means that for every 1 of these, we produce 2 of these. So for every 1 mole of A, we produce 2 moles of B. So it's a 2-to-1 ratio. And now we've canceled out moles of A. And now, after all our units canceled, we're in moles of our desired if we were to calculate this. But we're not going to calculate it because we have one more step to do. So we have step 3, which is our units of desired. Units of desired. So we want to know the units of this, which is mass. We want to go from moles to whatever units it is. I say units. In this case, it's grams, but it could be liters, could be concentration, could be lots of different things. So we have moles of B, and we want to cancel out our moles. So we want moles of B down here, and we want grams. So we want our grams to be up here. Grams of B. So now we just need to know how many grams are in 1 mole of B. Well, this is C12H5. We just go to the periodic table. I'm not going to go to the periodic table because we've looked at those elements before. Now we don't worry about this 2 here. So this 2 doesn't count when you do the molar mass. It's just the molar mass of just the compound, not this number. This number only tells you how it reacts with other compounds or its ratio of production or consumption of other ones. It just means that there's a 1 to 2 to 2 ratio in the reaction. This 2 has nothing to do with how many atoms there are here. So don't include this number in the molar mass. You'll definitely lose a lot of marks for that. Or hopefully not too many. So there's 2 carbons, which is 12.011, plus 5 hydrogens, which is 1.008. No, there's 6 hydrogens. That's okay. I'll add the other one. Plus a oxygen, which is 15.999, plus another hydrogen, which is 1.008. And the molar mass is 46.069. So 1 mole of B weighs 46.069 grams. Just double checking. 46. Yes. Okay. Good. Now we can do this all in one fell swoop. This is all one calculation. I'll show you how to do this. It's pretty simple. You just do 500 and then divided by 180.156. Then we multiply it by 2. Then we multiply it by 46.069. Notice I don't need brackets. Pretty much any calculator. I'd be surprised if that you would need a calculator where you'd have to put in brackets. Calculators are smart enough that they know bed mass or bed moss. If your calculator does require brackets to do this, let me know which calculator that is. I'd be curious because I really haven't seen any anomalies. We just kind of write it in as we see it. Okay, so 255.72. So that's what the calculator gives us, 255.72. Now we need to figure out what the units are. Grams of A cancels out with grams of A, so this is done with this. Moles of A cancels with moles of A. Moles of B cancels with moles of B. Since everything's canceling, you know we've done something right, and we're left with the units that we want. Grams of B. And what is B? B is ethanol, C2H5, C2H5OH. And then for full marks, we look at the significant figures. There's 4 significant figures here, which means our answer should have 4 sig figs. So 255.7 grams of C2H5OH. Sweet. All right. Moving along. So what we just did was stoichiometry using masses, grams, and moles. Now we're going to jump into solution stoichiometry. Solution stoichiometry is super popular. You're going to see solution stoichiometry like all the time. We're always dealing with solutions in the lab and whatnot. So let's jump into it. Okay, so our first question, what mass of BaSO4, barium sulfate, can be made from 10.00 mils of this 0.125 molar, that's what this M means, barium chloride, BaCl2, and an excess of H2SO4. And you have this chemical equation here. So this might seem like a mouthful, and it is. But look what we have. We have a chemical equation, okay? We need to know something about barium sulfate, mass, right here. And what are we given? We're given this stuff here. We're given information about this compound. We know that there's 10 mils, 00 mils, it's supposed to be a 10. And we know that there's this thing here, 0.125 capital M. So we're given information about one of the compounds. We need to know information about another compound in a chemical equation. This is stoichiometry, which means we can do this in 3 steps here. Step 1, we need to know how many moles of our given there are. And this is our given right here, our barium chloride, because we have information about it. We don't really know anything about this one. So we want to go to moles of barium chloride. Well, we don't have grams here. We have a volume and a capital M. And this M, really, it's a hidden unit. And every time you see this capital M, you should change it to moles over liters, because that's what it means. Moles over liters. And when we say 0.125 moles, we really mean their molarity, sorry, not moles, this is molarity, 0.125 capital M is 0.125 molarity. What that means is 0.125 moles per liter. But what that really means for stoichiometry is that 0.125 moles of this stuff, there is 1.125 moles for every 1 liter and I should write BaCl2 here. So that's what this means. This is a conversion between moles and liters. That's what that capital M is, and you should always change this capital M. Never leave it as a capital M. Always change it to moles over liters so that you don't lose these units. These are secret units hidden in this capital M, this molarity symbol here. So, and it really means there's 0.125 moles for every 1 liter. So this is our conversion between moles and liters. And we know how many liters there are, kind of. We know how many milliliters, but we can go from milliliters to liters. So step 1, we need to know how many moles of our desired there are. So we're going to go to moles by canceling out liters. Now we don't have liters, we have milliliters. 10.00 milliliters. So to get to moles, we first need to get this into liters. How many milliliters in a liter? You probably have to memorize it. If not, then it's on your cheat sheet for class, but there's 1,000 milliliters in a liter. Now that we're in liters, see that? We're in liters, we can cancel out, we can use this conversion here to cancel out liters. So we will put liters in the denominator, put moles, which is what we want, in the numerator, and there are 0.125 moles for every 1 liter. And I broke my own mistake here. I said we should always say what this is of, barium chloride. And I didn't do that. BaCl2, BaCl2. I'm talking and I'm writing and I'm explaining, but that's getting missed. BaCl2. Okay, anyways, this cancels out BaCl2 and liters. So liters cancels out here, milliliters, and we're left with moles of BaCl2. You know, I'm going to calculate this just because it's getting pretty long. So this is 10 divided by 1,000, which we probably don't have to do, times, oh, we could have done this in our head. Oh well, 0.00125, 0.00125, and the units that are remaining is moles of BaCl2. Okay, step 2, we have moles of our given, we want moles of our desired, so we'll start with our answer from the previous step, 0. I'm going to write this in scientific notation, 1.25 times 10 to the negative 3, because you got to move this decimal over 3 times, and this is a small number, so negative 3. Moles of BaCl2. Step 2 is where you really want to make sure you're writing moles of Cl2 here. And we want moles of our desired. What's our desired? This is our desired here. See, they talk about H2SO4, but it says we have an excess of H2SO4, so we have like a truckload of this stuff. So this is an excess, so it's not going to limit how much we make. This is our desired here. And is this balanced? This can't be balanced. Oh yeah, this is balanced. Barium, barium, sulfate. Oh, okay, there's no numbers here, so this is just a 1-to-1 ratio between these two. Since it's the same number, I would still write in the unit, or the fraction here. I would, even though it's a 1-to-1 ratio, so for moles of BaCl2, we want to cancel that out. We want moles of BaSO4, that's our desired. BaSO4, and 1 mole of BaSO4 is produced for or it reacts to produce 1 mole of BaCl2. It's a 1-to-1 ratio. Since it's the same number, it's the same number, but I would still write this fraction out just so you can cancel this. And I would stick to the steps, stick to the system, try not to do any shortcuts with not writing in units and things like that. If you stick to the system, then you'll always get it right. So this is the same number, 1.25 times 10 to the negative 3 moles of BaSO4, barium sulfate. Now step 3, we want the units of the desired, so we'll take the answer from the previous step, 1.25 times 10 to the negative 3 moles of BaSO4. Now we want to go from moles of BaSO4 to units. And what are our units? Oh, it's mass. So we want mass. So we got to convert from moles to mass. That means we want mass. So we want grams of BaSO4. We have moles right now, so moles have to go in the denominator so that they cancel out. Oh, not BaBO4, BaSO4. Okay, so we just need to know how many grams per mole are in BaSO4. Go to our periodic table first. Barium is way down here, 137.33. 137.33 plus 32 point, what's sulfur? 0.6 plus, and there's 4 oxygens, right? 4 times oxygen here is 15.999. 15.999, okay. 233.386. So 1 mole weighs 233.386. Just want to double check that. Yep. Okay. Alrighty then. So we'll take that number 0.00125 times 233.386 is 0.2917. 0.2917. And our units are, we cancel out barium sulfate, and we're left with grams. Oh, see what I did here? This is barium sulfate. This is barium sulfate. This should be barium chloride. Oh, that's right. This is barium chloride. This is sulfate. Okay, that's all right. Barium sulfate, never mind. We're good. Grams of barium sulfate. And lastly, for full marks, we got to check out our units. So we have 4 sig figs here, 3 sig figs here. We're just multiplying things, so we want 3 significant figures. So 0.92 grams of barium sulfate. Okay, I'll do another solution stoichiometry problem. What volume of 1.0 molar HBr is required to titrate 125 milliliters of 0.99 molar calcium hydroxide, CaOH2? And we have a balanced equation here. Again, this might look like a bunch of numbers and things, but we have a chemical equation. We want something, we want information about HBr. So HBr is here. This, we want the volume. That's our question mark. And we're given information about calcium hydroxide. So we have 0.99 moles over liter. Remember, this is a hidden unit, 2 units, moles over liters. And we're also given its volume, 125 milliliters. Now we're also given some information about this HBr. We're given that it's 1.05 moles for every 1 liter. But this is our desired because we want to know the volume with this one. So this is stoichiometry because we have a chemical equation. We have information about one of the compounds, and we want to know information about another compound. We have this information here, which is going to help us get the volume. Okay, so because this is stoichiometry, we will do our 3 steps. And step 1 will be the moles of our given. Here's our given. We want moles of our given. Now, where do we start? It doesn't really matter which number you start with, but see this number? This has moles in the numerator, and we want to cancel out liters. So it's usually best to start with the number, whichever number that only has 1 unit. That's generally a good place to start if you're not sure how to start. You could start with this number, 0.99, if that makes sense to you. But I generally like to start whichever number to do the conversions that doesn't have another unit. It's like if you have a number, see this has 2 units, this is a good conversion factor. It's good to, this is a good thing to convert units with. This one you can't convert units. It's just a straight up unit. So this is a good place to start. So step 1, we'll get the moles of our given. We're starting off with 125 milliliters. Now to get moles, we need to cancel out liters. So we got to convert that to liters. And we want milliliters to cancel out. We want liters, so milliliters in the denominator. 1 liter is equivalent to 1,000 milliliters. Now that milliliters cancel out, we're in liters, and we want to go to moles. So we're going to first put the units in first. Don't look at this number first. We want to do the units, and it doesn't have to be this direction. We want to see that we have liters here, so we got to make sure we have liters down here, and make sure we have moles on the top. Sometimes this is flipped, and if this is flipped, then we need to do 1 over 99. But in this case, we don't have to do that. So there's 0.99 moles for every 1 liter. Moles cancel out. Oh, again, I didn't write down our, our compound. It's instinct. I've done so many of these. For the first step, I usually don't. This is calcium hydroxide. This is calcium hydroxide. Calcium hydroxide. Calcium hydroxide. This is also calcium hydroxide here. Calcium hydroxide. Okay, and calcium hydroxide for both of these. Okay. All right. So everything cancels out. We're at moles of calcium hydroxide. Okay. So 125 divided by 1,000 times 0.99 is 0.12375. So 0.12375 moles of calcium OH2 there. And it's sometimes customary to put a line over how significant this number is to 2 decimal places. So this is our step 1. Step 2 is moles of our desired. So now that we use this one, our moles of our given, use the answer from the previous step to calculate the next one. So we'll start off with 0.12375 moles of CaOH2. This is only significant to 2 decimal places. Now we want moles of our given to cancel out. So we want moles of CaOH2 down here. And we want moles of our desired. So moles of HBr. And the chemical equation tells us that for every 1 mole of calcium hydroxide that reacts, it reacts with 2 moles of HBr. So there's 2 moles of HBr for every 1 mole of calcium hydroxide equals, I'll do this in my head, 0.246, this would be 7. 247, this would be a 4 plus 1, 5. 5, I believe. Let me know if I'm wrong in the comments, but I think that's right. Mental math, moles of HBr. Okay, step 3 is the units of our desired, and our units, I think, is volume. Is that right? Units are volume, so we want the volume, and we're also given this concentration. So we're given 1.05 moles for every 1 liter. So we'll use our answer from the previous step, 0.2475 moles of HBr, and we want liters because we want volume. So volumes are question mark. So we want volume in the numerator, which is in liters of HBr. And we want to cancel out this unit, moles. So we need moles down here, HBr. And this is our conversion between liters and moles with the concentration. There are, in 1 liter, there are 1.05 moles of HBr, which is pretty much the same number. So calculate that, 0.2575 divided by 1.05. So 0.2357 equals 0.2357 moles cancel out. So we have liters of HBr. And I believe we have 2 sig figs. This is 2 sig figs, so this is 2 sig figs. Go back to the answer to check. We have 3 sig figs here, but essentially 2 sig figs. 0.24 liters of HBr. This is a liter. Liters. Sorry, it's messy. Cool. Cool beans. All right. Moving along, this is our last example here of solution stoichiometry, last example of the video. Hope it's been helpful so far. I've gone through a variety of different types, so each example is very representative of what you can see on an exam. And this may come up as well. So we have a chemical equation, and we have this information about KOH. So we have 15.40 mils, it's a 0, and we have 0.610 molarity. And remember, molarity is actually moles over liters, so it's good to change that right away. And we want to do something, neutralize 20 mils of H2SO4. So we have 20.00 mils. And our question mark is this. So this means the concentration, right? This, when you have it in square brackets, and it's concentration in molarity. So this is our desired. We want to know something about H2SO4. This is our given. We have a chemical equation. So this is stoichiometry, and we can do this in 3 steps. So I'm going to do this all in, actually, I got to do this in 2 steps, but we'll do it kind of a quicker version since we've gone through this a lot already. So we'll start with what we're given, and we're going to start with the number that the quantity that only has 1 unit. So we'll start with 15.40 mils. We got to convert to moles of our given. So first we got to go from milliliters to liters, and we want milliliters to cancel out. We want in liters, and now that we've got the units in, we know that for every 1 liter, there's 1,000 milliliters. So now that we're in liters, we can get moles. And this means that there's, well, I'll do this first. So we want moles. Oh, I got to write in the compound. Holy moly. This is KOH. 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 This is KOH. Okay. Moles of KOH. That's what we want. And we want to cancel out liters of KOH. So we'll cancel those out. But we need to know the numbers. So there are 0.610 moles of KOH for every 1 liter. Now that we're in moles of KOH, we want to go, this is our step 1 here, right? This is step 1. Moles of our given. Whoops, step 1. Step 2 is moles of our desired. So this is our given, this is our desired, and there's a 2-to-1 ratio. Now we'll set up the units first. We have moles of our KOH, so we want that to cancel out. Moles of KOH. We want moles of H2SO4, because that's our desired, so that's step 2. Moles of H2SO4. And for every 2 moles of KOH that react, we need 1 mole of H2SO4. And step 3, so this is step 2. I'll write this step 2. Now step 3 would be units of the desired. And units are in a concentration. So this is if it's not obvious, then just calculate it and then do the step 3 after that. So I'm gonna solve for this first here. So 15.4 divided by 1,000 times 0.61 divided by 2. I think that's okay. All right. 0.004697. 0.004697. And what are our units? So moles of KOH cancel out. Everything cancels, but we're left with moles of H2SO4, which is what we want because that's step 2, get the moles of our desired. Now, step 3, this is kind of step 2 as well. Step 3, we want the units of our desired. So our units, see this is concentration. So this H2SO4, the units are in molarity, which is moles over liters. So we want to know how many moles there are in every 1 liter of this. Well, we have this many moles, but this is how many moles in how many liters? It's this many moles in 20 milliliters. So what we have is we have this many moles of H2SO4. See, we have moles, so we already have moles here. 0.004697 moles of H2SO4. And it's not this many moles in every 1 liter. There's this many moles in 20 milliliters. 20 milliliters. So we want to know how many there are in liters. We need to convert milliliters to liters. I'll show you another way how to do this as well in a minute. So we want liters in the denominator. We want milliliters to cancel out. And for every 1 liter, there's 1,000 milliliters. So that milliliters cancel out. And now look at our units. Our units are in moles over liters, moles per liter. So that's pretty sweet. It all works out. So plug that into our trusty calculator, 0.004697 times, divided by 20 times 1,000 is 0.23485, 0.23485 moles over liters. You could use a capital M, but that's the same. And lastly, of H2SO4, this is, of course, of H2SO4 as well. H2SO4. Oh yeah, sig figs. Lastly, sig figs. So we'll go to the top. We have 4 sig figs here, 3 here, 4 here. We haven't added or subtracted anything. We're just multiplying. So we take the one with the lowest number, so 3. So 0.235, 0.23, not 25, 235 moles per liter. All right, so if this part was confusing to you, you can also use the concentration equation where C equals N over V, where we have the number of moles. See, this is our number of moles here, number of moles. So to get the concentration, we plug in the number of moles divided by the volume. You may need to rearrange this equation. In step 3, you might need to solve for volume. If you need to solve for volume, then you just kind of rearrange this, or you can do this way. Either way is fine. Look at it and see what I'm doing and get it, and then get a perfect exam. Maybe you can get by that way, but the chances are you really need to work through these problems. And hopefully this has given you a great handle on how to work through the problems so that you won't blank out and you'll do very, very well on your stoichiometry exam. Thanks for watching. Really appreciate it. If you got some value from it, please consider liking this video as it really motivates me to make more. And I'll see you in the next one. Cheers.